So today I'm going to talk about building big systems. That's already a big area. Little things and big things. So I'm not going to say everything, but I'm going to pick some highlights. I'll mention the Christmas tree analogy. First, some starting points, some basic principles. Then an industrial example, which is a very neat example that really happened. And then three main things if you want to build a big system that can be scalable. And then I end up with some little highlights, some large-scale phenomena, things that happen in big systems. So I'm a computer scientist. So actually, I teach Erlang in my programming course. And so every year, 200 students are coming out of UC Louvain who know Erlang. It's good. More than in Sweden, maybe. Unfortunately, KTH is not doing so much anymore. It's pretty bad. So it's part of my programming paradigm course. I also have lambda calculus and stuff. Some of the ideas in this talk are coming from a collaboration I have with a company called P&Sol, Predictable Network Solutions, in particular Neil Davies and Peter Thompson. So these guys are in the UK, near Bristol. And they're typically some of the many companies, and also you are part of this community, who keep the internet working, but who are not mediatized, because a lot of what they do is kind of hidden behind NDAs and things. So they've saved a lot of big companies, and they have a lot of good ideas. So some of the ideas I'm going to talk about actually came from them, that were in their head. So we're trying to disseminate what they have kind of floating in their heads. So that some of this stuff I'm presenting here, it's the first time that those things are on slide. Okay, so you guys will see it first. So this is what we're going to talk about. So this is a famous diagram from a book from '75 on general systems thinking. So you have complexity and randomness. On the left bottom, you have machines, which is organized simplicity, things like mobile smartphones. Of course, the complexity gets a little bit higher, but they're not so random. And up on the top, you have gas in boxes, lots of unorganized aggregate. And in the middle, you have the interesting stuff. And this is almost unknown. So computer scientists and you guys are the ones, we are the pushing the boundaries of this. So what I'm going to say today is going to be in that white thing. But what I'm going to say today is only to be little bits and pieces. So system design is like a Christmas tree with many, many ornaments. So there's a Christmas tree with burning candles. I'm not sure if that's even allowed in Europe anymore. But so I'm only going to present a few of the prettiest ornaments today, but there's lots more ornaments, so there's going to be references at the end. And we're still working on a lot of stuff, so try and get everything, all the ideas together coherently. So you're going to just see a few of the nicest little decorations. Okay. Some starting points. First of all, if mechanics has Newton's laws, scalability also needs some laws. So there is the first law, and this is what makes it really interesting. At each new scale, new things happen. So I have a quote from a very nice movie called The Maltese Falcon. We have the detective Sam Spade, Humphrey Bogart, talking to Caspar Gutmann, who was called the Fat Man in this book, who was basically one of the bad guys. And Sam Spade wants his money, $10,000, he says, but he gets 10 $1,000 bills. We were talking about a lot more than this. Yes, but one real dollar is worth $10 of talk, okay? Once you get to the reality, scale becomes completely different. No problem is ever solved at all scales. Every scale brings something new, okay? So that's the first thing to get you in the mood. How does the situation change as the system grows? Well, actually, there's a really interesting quote from Goethe, of all people, a very smart guy. So this is coming from a book, Conversations of Goethe, with Johann Peter Eckermann. Imagine a green plant shooting up from its root, thrusting forth strong green leaves from the sides of its sturdy stem and terminating in a flower. The flower is unexpected and startling, but come it must. The whole foliage has existed only for the sake of that flower and would be worthless without it. So the whole thing, while it's growing, you see nothing until the flower appears at the end. Okay? So that's a very interesting analogy where you don't actually know where you're going, but there is a goal. So this is actually connected to the first law. When you build big systems, quantitative difference becomes qualitative difference. A growing system is actually moving towards something. And this actually only really works if your system is well designed. So if you follow some good principles, your system will do interesting things. Okay, we have very recently a very a kind of unexpected and I would say disturbing example of this, ChatGPT. Okay, our goal is to make sure it behaves reasonably. What does that mean? We don't really know. It's like planting a flower, building a big system. All you can do is help it grow, maximize the chance of a good outcome. But what is that outcome? You don't really know. If you grow a rose bush, if you let it grow huge, you can have big climbing roses. We have in our garden this huge rose, and they become like trees with huge trunks that are like wood, which you don't see when they start, okay? So that's a kind of analogy for big systems, okay, to get you in the mind. So don't worry, later on it will get much more technical and you will be pleading for me to be more philosophical, but I will stay a little bit more philosophical now. When building big systems, there are two ways of doing things that are like frauds that you should not rely on. So I have to warn you against them. I will expose them. The first one is induction, inductive reasoning, which means past experience is a guide for the future, okay? If you're building a system bigger than anything you've built before, probably new things are going to happen, and the old way is not always going to work, okay? And there's this very nice concept called black swans, which I'll mention in a minute. The other one is probability distributions. This is something that scientists and mathematicians love. Probability distributions. You simplify analysis. You know, it's so nice. There's so much theory, but they don't really exist in practice, okay? It's a very strong assumption. It means you have a frequency limit as the number of trials goes to infinity. That's a hugely strong assumption. So I will mention, this was known for a long time, and there's a very smart computer scientist called Edgar Dijkstra who has explained it. So I will introduce Dijkstra's demon. So let me talk about Dijkstra's demon, Dijkstra or Dijkstra in Dutch. And Dijkstra's demon cannot be exercised because this demon has an essential role. So unlike Maxwell's demon, who has been exercised, this one will not be exercised. So consider a guarded command. It's like an if statement. You have Boolean guards and statements. B1, if B1 is true, you can pick S1 up to Bn. So the idea is to select any true guard, non-deterministic choice, okay? The execution selects any true guard. What can we assume about that selection? Actually, we cannot assume anything. We cannot assume fairness. And what Dijkstra says, the most effective way out is to assume the machine, the unbounded machine, not equipped with an unbiased coin, so no fairness, but with a totally erratic demon. Okay, so he talked about the demon. This was in 1976. The PDF of this book is on the net. Really nice. Don't use probability. Fairness is probability, basically. But you have to verify all paths. And Dijkstra's demon will find the path that will kill you if you have not looked at all paths, okay? So be very wary about probability. Sometimes you can use it, but only when combining independent events. But most of the time you cannot use it. Another point, this is now relating on induction. You know the story about the farmer and the turkey, the famous story. There's this turkey, every day the farmer feeds the turkey, and the turkey is so happy. This farmer, this good guy farmer comes and feeds him every day. And after some months, the farmer comes and chops off the turkey's head, okay? So the turkey was not a good idea to use induction to deduce that the farmer was a nice guy, huh? Okay? And I remember, for example, the year 2000 bug. It's still very strange for me with all the gray hair to see that we're in 2023. I remember in the 1980s, the year 2000 bug, okay? Too big to fail. It was far away, but it arrives. Big things arrive. Nothing is too big to fail, okay? All systems, computing systems, have finite resource limits, but usually you're way below them, so you don't really feel them unless you get to push against the edges, okay? So you feel like you have infinite power, and it will fail if you need that power, because you will notice you don't have it. So the black swan is an unexpected event that is obvious in hindsight, but not at the thing. Large systems, you have to survive unexpected events, and I will talk about that. So there's a very nice book by a guy named Nassim Nicholas Taleb, Black Swan. If you haven't read it, it's very nice, okay? So how do you survive black swans? Okay, before going to the principles, let me give you an industrial case study. This case study comes from P&Sol. A major MNO. MNO is a mobile network operator. This was a real big one. I will not mention the name because I'm being recorded here and I want to live after, okay? And so I will not mention, but this was a real thing. So they deploy small cells. So the small cells are little radio access nodes with short range, and they connect into this whole network infrastructure. And this company was introducing this consumer DSL broadband, okay? And, okay, so they were testing it, it worked. A few hundred users. A month or two before the launch, they tried scaling it up, and the whole thing, all the small cells started failing. So they panicked, and they brought in P&Sol, and it's a very important thing they learned. Okay, so these small cells were failing. So here is the diagram. So on the left, you have the users at point A with little small cells. You have the control points. Then you have the wholesale access network, the national interconnect, and then the MNO core. So the core of this big, huge company, who will remain nameless. Okay, so it's not just one company. There's many companies, and when you connect the two pieces, there's a contract on the performance, that there's a compatibility, okay? So when you communicate from one person to the other, it starts at a small cell, it goes all the way up to the reference point, and then it goes back to the other small cell, okay? So the MNO, all the contracts were signed, and they believed that the contract would deliver the service, but no, it didn't. Okay, so to make a long story short, P&Sol was measuring all the packet delays between the different points using the approach. So I'm not going to say much what it means, the delta Qs here. It's basically the delay as a function of time. If you look here at this experiment, this is a part of the packet delays. Zoomed in from 590 to 600 seconds, you can see there's these spikes, okay? So, for example, the big spike goes up to more than 0.4 seconds, okay? Delay, and they can last for seconds, these spikes, huh? And the small cells were failing because of that. And the reason is because small cells have control loops. And if the control loops are too slow, the small cells, they don't like that, okay, and they fail. But the problem was nowhere near the small cells. So why do you have these weird spikes? What is causing them? A typical big system effect, okay? So here, the explanation. If you look at the rising, the one at 595, it rises very fast. you see lots of packets. So it's basically filling a buffer. So basically you have a temporary increase in load, causes many, many packets, much more than the queue, the component can absorb. So they all go into the buffer. And then the overload disappears, system is back to normal, but you have this full buffer, and it slowly empties, okay? The buffer is filled very quickly, but the delay it causes is very long-lasting. Temporary overload causes buffer to fill up quickly, but emptying takes much more time. That seems, that's understandable. You see where that problem is coming from, huh? So why did this big company full of super smart engineers who are used to building businesses not realize this? Well, we'll see. So a queue is forming in this network, in the middle somewhere. Now we're nowhere near the small cells, okay? It exhibits temporary overload. So this is in breach, of course, of the contract. There was no, but where is it coming from? The problem is this queue is delaying all the traffic, and the root cause is that the subsystems are actually not composing because they were not really designed right. The MNO believed they only had to match bandwidth. Sure, if my system has a certain bandwidth and it's coming in and it's less, fine. But you have fluctuations, okay, which were not correctly taken into account. And now I get a little bit more technical, because this is an important lesson. A small thing can have a huge consequence. So here now let's understand a component. So this thing C is a component, has an incoming message and an outgoing message, okay? And there's 4 parameters that are interesting here. There's the offered load, so the number of incoming packets per second, which is a function of time, the buffer size in the component, and then there's 2 outputs, which is the delay between input-output and the failure rate, because some of the packets will be dropped if you cannot put them in the buffer. So you have these 2 inputs and 2 outputs. And how does this work now, really? And now, a little bit of queuing theory. So we consider the component as what's known as an MM1K queue. So you have a queue of size k-1 and a server which does the actual work. Packets are coming in. The first M means they come in exponentially distributed. The second M means the server, the time to service is also exponentially distributed. The 1 means there's only one server, one message at a time, and the K is the buffer size. If a message comes in and the buffer is full, it's dropped, okay? So the offered load, we will normalize it, lambda over mu, so it's the little letter A, which I will talk today. So normally, you can handle a load of 1, right? Which is, the incoming is the same as the server size. But when packets come in and the buffer is full, they're dropped. So how does this relate to our little small cells example? Well, the value 1 is very important here, okay? If you have a low load, less than, let's say, 0.8 or so, turns out the failure rate is very low. The delay is very small. It's basically 1 is the minimum delay. Adjust the service, so the buffer is almost empty. Underloaded component, very nice. But once the load gets too big, but not even 1, 0.8, it's because of the fluctuations. The failure rate goes way up, because the buffer can be full. The delay increases to K when the buffer is very high. So there's a kind of switchover between 0.5 and 1. As the load increases beyond 0.5, the system quickly gets very bad. Even a temporary overload causes a big, long-lasting degradation, okay? So because of the fluctuations, the daemon has made a system have a problem here. Okay? Okay, so that's our first example. You can see that little things, big buffers are actually bad. Huh? If you buy a NIC, network interface card, and the manufacturer is boasting how big the buffer is, no. It will only work well at very low load. If the buffer is big, the delay can be very high. Okay, so that was just an example to get your neurons kind of in tune. Now let's look more principled way. How do we design systems? Fundamental issues of system design important for scalability. And I'm going to focus on 3 particular ornaments. One is temporary overloads, the second one, permanent overloads, and the third one is the nasty problem of taming nondeterminism, okay, which is basically poisoning the whole system. So I will not really talk about fault tolerance, increasing performance. That's not the problem, okay? Anyway, you guys know this stuff very well. I mean, who am I to talk about fault tolerance in front of Erlang people, okay? You guys know this stuff very well. So I'm not going to teach you anything, but maybe you learn something about how to structure the system, okay? The first thing is temporary overloads, okay? Okay, now let's talk about you as a designer. Okay, so you're a nice system engineer, very responsible, good guy. You're prudent. You overdimension the system. Of course, this does not solve the problem of overload. There will always be overload. So you have to live with it. So that's the point. Even if you overdimension, in fact, the problem gets worse. People think the system is better than it really is, and they will pound it. And it better be able to handle that, okay? So the question is, how to design your system to be predictable when the overload happens, and it will happen, huh? So there's 2 cases that occur, and both of them occur a lot, and they require different approaches. So first is the temporary overloads, and this is typically what we saw already in the small cells example, but then you have permanent overloads, and that I will explain a little bit later. So the system must behave reasonably on temporary overload, and there's 3 design rules. First of all, when overloaded, the system may behave badly while it's overloaded, but it must never break. That means when the overload goes away, the system has to go back to normal. I think many people kind of understand that, and there's some good examples in Erlang-based systems. I show this emblem here, fluctuat nec mergitur. Not sure you know what it means. This is the devise, the slogan of the city of Paris. And it's a boat. And what it means is, it is tossed but does not sink, okay? That's exactly what that first rule is. When they're overloaded, the system will be tossed in the storm, but it will not sink. When the overload goes away, the system goes back to normal. We can also say the system is ballistic. That means like a ballistic missile, when there's no feedback control. It behaves predictably in overloop. So you must design it in this way. And if you do that, good things will happen. And the second, when overloaded the system, you need some guaranteed minimum functionality. And there's also some nice stories about that. Routers that provide 0 functionality while they're reconfiguring. There was a case where such a router was envisaged for the American military's thing called Future Combat Systems, which was a big program in the early 2000s. And this top-of-the-line router from a company that I will not name, during 30 minutes of reconfiguring, no messages passed. But in the military, they have this thing called EAM, Emergency Action Messages, which must always pass. Okay, low bandwidth must always pass. These are messages of the form, please cancel the launching of the nuclear missile. Okay, this message should always pass, okay? But it didn't do that. So, predictably, the US military did not sign a contract with this company that will remain unnamed. Finally, you still need to be able to manage the system when overloaded. So if you do this, if you follow these 3 rules, your system will be very nice when it's overloaded. Okay, and I want to give you some intuition on that. It will be predictable. So again, we're going to go back and look at this wonderful MM1KQ, which gives you a very good model that corresponds to reality. It turns out the worst situation happens exactly at the edge, when the load is equal to 1, when you're right at the maximum that it can handle. So it's not yet really overloaded. You have your system becomes wild, okay? It's very interesting. The system will be much more stable when it's massively overloaded than when it's slightly overloaded, okay? So here's the way I like to see it, is you have a cliff. So this is one of the cliffs of Dover, okay, beautiful cliffs. So on the left, you have low load. Your system is stable. You have superposition principle. Everything is linear. Everything is wonderful. Practical latency is low and predictable. On the high load, you also have a stable system. The behavior is independent of the applied load. You have a very high loss. The output is constant. It's equal to 1, okay? But the input is much bigger. The output is equal to 1. And the packet latency is high, and it's predictable, because the loss decision is made at the entry of the system, okay? If the buffer is full, you drop it immediately. The interesting bit is the middle one. When you have critical load, in this position, the latency will wildly fluctuate. Your system is just going wild. So the point is, don't worry, it's not a problem. If the load gets worse than that, things will not get worse. They will actually get better, okay? So here's a technical analysis. So this is derived from the equations of a MM1KQ, which I laboriously figured by hand. I think this is right, okay? If there's a mistake, you will tell me. So 3 cases: low load at the edge, A equal 1, and high load. So this is a cumulative distribution function of the system delay. So the horizontal is the delay, and the vertical is the percentage. So the percentage of packets that have delay less than or equal. So notice at low load, when it's less than 1, you have this negative exponential that pushes to the left. So the delay is very small, and it tends to 1. So 1 is the minimum delay, because the component has a server that takes 1 unit. So it goes to that. So that's very good. The failure rate is very small. It's this number here, almost basically 0. And at very high load, again, things are predictable. You have also an exponential, which is 0, but then it rises at the end, and again, it pushes everything to the end. So the delay is k. That's predictable, right? It's always k, always. So very constant delay. The failure rate is very high, a minus 1 over a. So a is very big, 10 or 20 or more. This gets to 1, but it's predictable. But in the middle here, you have this basically linear. Well, it's basically a step function, but assume it's linear here. That means the delay can have any value. And the probability is the same for all of them. But the failure rate is still pretty small, but the delay is wildly fluctuating, okay? The point is, no panic. This is normal. This is a well-designed system, okay? At the edge, when it overloads, as all systems will, okay? And another way of looking at things, which people usually do. So this way of looking at things is less common, but this way is a way that people do it at PNSOL. It's very useful, as you see. Another way is what's called the throughput latency diagram. So you have this curve that is graduated in load, okay? And again, you can see the different areas. So the green part is low load, linear behavior. The medium load is when it gets to 1, so you have the maximum throughput. And at very high load, the latency is increasing, and you actually start rejecting tasks, okay? And I have to show you then this system, which is very famous in the Erlang community, the XD301 ATM switch, which has the infamous 9 nines. I'm not sure if I believe that. 9 nines availability, okay. It means 30 milliseconds per year not available. Hard to measure, okay. So, but look at this graph here. Offered load going up to 1,000%, so 10. A is equal to 10. And then the throughput. Notice performance goes up linearly up to the limit, and then it slowly goes down because of the handling of the rejected calls. So this is a typical example of a well-designed system, and this kind of system, it's interesting that it's much easier to design such a system in Erlang than using other systems, okay, than other languages. So this is typically how your system should behave when there's a high overload. Okay, so that's the first bit. But we're not done yet by far, because we've only handled temporary overloads. Okay, so that's normal. You're happy, it handles temporary overloads. Everything is great. Until the temporary overloads start happening too often. The people are getting very demanding, and they think your system is next to the best thing since sliced bread, and they're really using it, and now your system is having a problem because it's always overloaded. The approach we did in the last section doesn't work anymore. We need another idea, okay? We have gone to another level. And the other idea is you have to worry about timescale issues. So the action to be taken now has to be taken at a different timescale. And the way to do that is to build your system in multiple levels. So I'll explain that. And then it's critically important to know what each level should do, and that's called mitigate, or when you hand over control to the higher level, and that's called propagate. So, of course, Erlang has a lot of support for this kind of approach, but be careful. The levels have to be truly independent and separate, okay? So it's an abstraction level thing. Of course, Erlang processes are independent, but the whole part of the system that is doing a second level must be independent of the first completely, and so on. So the whole system kind of looks like this. You have a base system satisfying QTA, specification, quantitative timeliness agreement. System 2 will detect when there's a QTA breach, QTA1 breach, and it has another QTA2. And when there's a QTA2 breach, then system 3 takes over. And 2 and 3 are working at different time scales. That means they're in a different world, actually. They're like in a different universe from the base system, okay? So here's a nice little example that worked out. Supermarket. Here we have a supermarket, entrance, 4 cash registers, you have a queue of people. So the little green dots are people waiting, customers that queue up. So the QTA is less than 5 customers are in line, okay? So what happens when you have too many? Well, actually, supermarkets are built using this approach, and you can see that the software and the human organization merge kind of seamlessly here. So the bottom level is the supermarket here, longest line less than 5 customers. If you breach this, you go to the second level, and the QTA of the second level is that you have not more than 50% of QTA1 violations. So there's a human usually who acts here. What can you do? You open another cashier station, you open a self-service, you open the bar, you set off the fire alarm, everybody runs out, solves the problem, right? Usually you don't want to do that. But maybe that's not enough. Even doing that, you have a problem. Well, then it becomes kind of a global problem. QTA3 is something that is solved at the level of the supermarket chain, okay? They will study that. What do? Enlarge the supermarket, open another one, close the supermarket, whatever, So each level escalates the solution at a different time scale. So the point is you have to think carefully of time scales, okay, for this approach. And the critical question at each level is, when do you go to the next level, okay? So each level has its own QTA. When you go to the next level, so by default you don't. You stay at the level and you solve the problems at your level until you cannot do this anymore. For example, you might have to implement multiple strategies that start conflicting with each other, or maybe you just don't have enough resources and it would be too hard to get more, then you propagate. And the second criterion is the time scale. For example, if solving the problem requires reconfiguring the system, or things like elasticity, which take time, which on an order of minutes or hours, or a human in the loop, that's a totally different world, okay, than a piece of software running. So you have to do it at the other level, at the next time scale. Okay? And an important kind of hazard, thing that can happen, is called a correlation. And there's two kinds of correlations. So these are the nastiest kind of problems. So external correlations are really the worst. A natural catastrophe happens and everybody phones, okay? Or aliens are sighted over Stockholm and everybody goes to the highway to go to their country cottage. So the highway is saturated. So that requires, so that's an overload of a severe nature based on an external event, but that can take time to solve. But then you have internal correlations. This is kind of problems in system design. You have a planned system upgrade at midnight. There was an example in a previous talk about things happening at midnight, and maybe some very devoted employee was doing lots of recompilation at midnight, and then you have a problem, okay, at midnight. So timescales. You have to have timescale, multiple timescales. So the base system follows its 3 rules. And then the next level is, so this is milliseconds, micro or milliseconds. This one is seconds, then hours to days, days to years. And you might have to put a human in the loop or reboot the system. That is a totally different world. You don't want to mix timescales, okay? Things that happen in milliseconds, things that happen in minutes, those are 2 different things. You don't want to mix them. They should be treated independently. Okay, so that's the second thing. So for that, I have given you some intuition on handling temporary and permanent overloads. But I don't know how much time I have, but another one is now a more general problem. The general problem is called nondeterminism. And it's, again, going back to Dijkstra's demon. So you cannot exorcise Dijkstra's demon, but you can limit his range of action, okay, a little bit. This is nondeterminism. So nondeterminism is defined as a choice that is made by the program that cannot be made by the person who wrote the program, by the developer. It's made by the program, and so the developer has very little control over that. Notice every single Erlang process is a source of nondeterminism. I'm not sure that was really the right default, but in the 80s, Joe Armstrong and company, they already did a very good job with what they did, but still, there's a lot of potential nondeterminism there. Also, commonly used distributed algorithms, like consensus, which is widely used, are inherently nondeterministic. Consensus, a whole bunch of nodes, each node proposes a value, the algorithm runs, and one of the values is chosen. That's inherently nondeterministic. That, in my view, is bad. So in my view, consensus is evil, okay? Don't use consensus. So how do you not use consensus? Also, debugging these systems. I mean, lots of war stories where you spend the hours and days getting rid of problems because of nondeterminism. Probably you have stories to tell there, okay? So I'm not going to tell you my stories, but it's really hard. You don't want it. But the point is, can we reduce that? How much of it is really necessary? Actually, Erlang is a real good example. Much Erlang code is actually deterministic, even though the processes are potentially non-deterministic. Behaviors are very deterministic internally. So my claim, and this claim has caused arguments between me and people, is that most of the non-determinism is superfluous in a distributed system. So here, let me explain why I think this is true. In my view, you only really need non-determinism at the system boundary, where the system talks to the real world or external world. So here in this blue-gray rectangle, you have a distributed program. And when it receives a message from the outside, the message can arrive from multiple points. And depending on the timing, one or the other message arrives first. So the one that arrives first is not chosen by the program, but externally, so that's non-determinism. And in the other direction, you may also have to make a choice. for correctness, for causality, you may have to choose, and that is not something that the program can choose. It has to choose because of the external world, okay? But inside here, I claim you can write things as pure functions in the sense of lambda calculus, and they're deterministic. Now, I say that to distributed systems people, and they will look at me and they say, that's totally bogus, okay? What about concurrency? This is concurrent. What about there's messages passing between these nodes? They're asynchronous. Of course, asynchronous messages break for the functionality property, right? That's a no-brainer, right? Actually, that's wrong. A functional system can have asynchronous messages. And here's the simplest way I can find to explain that. So here on the top, you have a functional, pure lambda program. So it could be Haskell or even functional subset of Erlang. It could even be a concurrent subset of Erlang as long as it's deterministic. And you have this really amazing property, Church-Rosser. No matter what reductionary you do, the result is the same. So here's an example. Y is f of x, z is g of y. So the y output of f goes into as an argument in g. Fine, okay, f and g are functions. Now I make this concurrent. Y is f of x runs in a thread. Z equals g of y runs in another thread. Well, we can still run the same program. How does it work? We add data flow synchronization. So the g is z of y. If the y is not yet computed, you just synchronize. You wait until the y is available. And it's perfectly correct. You have a beautiful, functional program. And it's concurrent. And now we make it distributed. We put these two threads on different nodes. Now the binding of y causes a message to be sent. And there's no reply. It's an asynchronous message, okay? And this G needs Y, so it waits until the message arrives, just to receive, okay? Notice distributed functional programming, it's pretty clear it can still be purely functional, and it has asynchronous messages and concurrent. So, and here's another example. So here I have 3 nodes. So this is using some weird pseudosyntax that's a mixture of Oz and other things. So here I produce a stream. I map one stream to another, S1 to S2. And here I create an accumulated sum and have another stream. So a stream is basically a list which is being created incrementally. And an agent is a tail recursive function. So S is equal to prod1 will be running on node 1, N1. And this one, another one, map on node N2 and 3. So the S1, S2, and 3, they're basically asynchronously, it's like TCP or whatever, there's a pipeline of messages being passed concurrently between the 3 nodes, okay? Perfectly functional, okay? So the conclusion of this is that, so this is my opinionated view on the right way to build systems, and this holds for both the permanent and the temporary overloaded systems, and it makes it much easier to write them. So internally it's distributed functional, which is not a problem. It's only a problem where you interact with the external world. So the whole part of the system, spread over many nodes, that you develop is as a functional program. And I think with a little bit of discipline, that's actually quite easy to do in Erlang. You just have to make sure your message patterns are deterministic, okay? Of course, choose carefully your distributed algorithms. So my view is avoid consensus. My view is in 50 years, no one will be using consensus anymore. The analogy is internal combustion engines. Do you know that's really how bad they are? You take a high-quality source of energy, which is gasoline. You convert it into heat, which is the worst quality of energy, and then you laboriously take a part of that heat and turn it into moving wheels. So you make a detour through this really bad, low-quality source of energy. Isn't that kind of brainless? Well, that's the main invention of the 19th century, okay? Now we're moving away from that with electric cars. My view, consensus is similar because it's inherently non-deterministic. You have this beautiful deterministic system. Well, you introduce this really nasty non-deterministic operation right in the middle of it. You poison everything. And then you try to make it work after that again, okay? I'm just as brain dead as internal combustion in my view. So yeah, I can, the nice thing about Keynote is I can tell you my opinion, okay? And if you don't agree, I would love to argue with you. In fact, you can all very often avoid consensus. There is, in fact, a data structure called the CRDT, conflict-free replicated data type, invented by a group of people around a guy named Mark Shapiro. Actually, it's quite highly used in Erlang. The React database has a lot of CRDT support, okay? So the Erlang community is actually very well positioned here. So is this really the right way then? Actually, I would say yes. Look at big data analytics. MapReduce is purely functional semantics. Implementation, of course, is not functional, but that's okay. The semantics is functional. In Erlang, it's clear. Being deterministic is good style in Erlang, clearly. And personal things. So me and my student Christopher Mickeljohn, we invented a system, made a system called LASP, which is a program, distributed program with CRDTs talking to each other. Really nice, scalable. We actually scaled it up to 1,000 nodes. So Amazon got quite a bit richer because of that, but it was the EU paid for it, okay? Okay, so that's the main ornaments, but I have a bunch of little things. Sorry. So I have a little bit more time, right? So I have a bunch of little things I can say. There's lots of little neat things that I want to say. And there's big systems are really strange. I mean, the proof, a human cell has 10 to the 14 atoms. And it's an amazing system you can build with 10 to the 14 atoms, okay, this living cell. Well, big systems have amazing kinds of behavior, and I'll show a few of them. And one of the really interesting ones is Buridan's principle. So if you have not seen this, this is really a mind-opening idea. So this is a medieval philosopher, Jean Buridan, one of these scholastics. He stated that an ass placed equidistant between two bales of hay must starve to death because it has no reason to choose one bale over the other. So the ass is completely rational. An ass is also known as a donkey, by the way. But in the olden days, people called it an ass, so I kind of like the old terminology. Okay, so what does that really mean? It means you have a system that has to make a discrete decision, yes or no, from a continuous input. A continuous input, any number from 0 to 1. And the theorem is the discrete decision based on an input with a continuous range of values cannot be made within a bounded length of time. There's always values for which it will take arbitrarily long. And you see this in real systems, in elections. If the election is very close, it takes longer and longer to decide. Typical example, the US presidential election of the year 2000 went eventually to the Supreme Court. They were counting and recounting Florida, and they were looking at each vote. Is there a hole here or not, okay? And it took really long. But example that I know very well, a jury decides whether a student passes or fails. Okay, so the student is very close to the edge, but does he go over it or not, okay? And all the professors talk, does he really fail this course by a lot or not, etc. It becomes harder and harder. This can be proved fairly straightforward. It's a little bit subtle, but it's actually worthwhile to see how it's happening here. So horizontally, you have the continuous input from 0 to 1. Vertically, you have the decision, so 0, 1, okay? So normally it should be only 0 or 1. And there's a curve, AT of x. It's showing the progress of your decision making, okay? So at time t, with starting position x, what is the decision? And so it's continuous, of course. So the function has to be continuous. You cannot skip from one because that's not reasonable. If the input changes a little bit, then your decision-making process will only make a small distinction. So A0 of x is just a 45-degree line. You know nothing. A1 of x, you're starting to decide, okay? A2 of x, you have already decided for a few of them, but for these in the middle, you don't. But notice, because this function is continuous, there is always, for every value of t, it has to move from 0 to 1. So there's always going to be values in the middle, okay? Of course, maybe not very many, but they will always exist. And this is something you see in big systems. In a distributed bank account, even. When you take money out of an ATM, which is owned by another company, maybe that money does not immediately come out of your account, okay? But this doesn't usually happen to people, but companies, for example, who make thousands of transactions in all directions all the time. Does that company have a positive or negative bank account? That's a hard question. And the voting system, which I mentioned, who wins the election? So the input data is continuous. As we get near the decision boundary, more and more information has to be pulled in from the whole system, okay? And eventually the whole system will be involved, like in the voting. So how do you handle that? Prevention or cure? So first of all, stay away from the boundaries. Don't snoop around the boundaries if you can avoid it. But sometimes you have to get there. Well, try to prefetch information or do escrow. For CRDTs, this is an idea that has been used a lot because consensus is this one-stop shop decision-making thing, but CRDT makes the decision in a much smarter way. And there are ways to do it where you do some kind of prefetching, okay? So that's one effect. Let me give now some more effects. So there's a bunch of them. Dominoes, giant components, epidemic cascades, tipping points. Tipping points are really nice, but I somehow couldn't squeeze them in, I'm sorry. But domino effects, for example. So this actually also was in the news recently. Assume you have a real-world network, which is modeled as a directed graph. So there's nodes with arrows between them. And a strongly connected component is a subset of nodes such that there's a directed path between any two nodes. And it's maximal. I mean, you cannot add more nodes. It's basically all these nodes have paths between all of them. So this actually can reveal a weakness. And the example that happened very recently is bank loans. So there's an arrow from one graph to another if the bank depends on the bank. So if I, as a bank, lend 10 billion euros to some other bank, that puts me in a position of weakness. Will the other guy pay me back, okay? And that happens in cycles. You would think, why do banks do that? But they're always doing that. And this is a well-known thing. This has been studied. This is coming from a book called Networks, Crowds, and Markets, but originally from another article. The network of loans among US financial institutions, so there's a strongly connected core here. And if one of the banks fails here, well, it fragilizes lots of other banks, which may fail, et cetera, like dominoes, okay? And if you have been reading the news, you have seen that it has happened very recently in the US. You think, why do they organize it? Because banks, they don't really care. As long as the money flows, they're happy, okay? Another example of weaknesses or big system effects is the notion of a giant component. So consider a social network where all the nodes are people, all the people on Earth, and there's an edge between two people if they are friends or if they know each other, okay? Is this graph connected? Well, probably not, because you will always find some isolated tropical island where people have been living for generations and they don't know anybody, okay? But still, many people have friends far away. I have friends on the other side of the world that I don't see very often, okay? So this is leading to the notion of a giant component. So you have a component, so a connected, like the strongly connected component, a connected subgraph, and almost all real-world networks have a component, a single component that has most of the nodes in it. Most is like 50% or 80%, some high percentage. And there's almost always exactly one, of course, because if there were two, it only takes one connection for them to collapse, of course, huh? And this has happened in the past. So the famous example is when European explorers arrived in America. So Pizarro, when he arrived in South America, caused an enormous collapse of two giant components with massive effects, technology, disease, epidemics. So this can happen a lot, okay? And it leads to another point, which is consistency. So in large, big systems, you have lots of data, and the data will always be inconsistent. Consistency is a mirage. Forget consistency if you have large data, even tracking real-world changes, okay? So let me give you two examples. One is very well known. It's called the CAP theorem. The other one is less well known. It's called pluralistic ignorance, but it's maybe even more important. And you cannot really correct it. Consistency, it's like failure. The Erlang people know failure is good. The failure is normal, right? Absolutely. Java people will lose sleep on that, but not Erlang people. Well, the same for consistency. Consistency doesn't exist. Inconsistency is the reality, okay? So the CAP theorem is a famous thing. I won't spend too much time. So you have three properties for a big distributed system. Consistency, so all the operands are atomic. So there's a total order among the whole system. Second, availability, you request of the system, it replies. And third, partition tolerance. Inside the system, messages could be lost temporarily. Well, you can only pick two of those three, says the CAP theorem. And you can prove that. For example, if you have C plus P, you will not have availability. All the requests that return will be correct, but some will not return, okay? If we assume that all partitions are eventually repaired, which may be reasonable, then all requests will in fact return a correct answer, but it may take a long time because it depends on the repaired, okay? So that's well known. But it's not just partition tolerance. This is actually a more important issue. This is a thing that is noticed in the real world, but exists on computer networks, called pluralistic ignorance. You can have a huge network which is connected, and different parts of the network will have inconsistent views on something. Okay? Well, why? Because maybe there's a small bottleneck and the information doesn't really flow, or maybe the ones at the edge of the bottleneck are not letting the information flow. So in the real world, repressive governments do this, okay? They love pluralistic ignorance, keep the people ignorant, and nowadays, information bubbles form in social networks. Okay, why? Because Facebook's algorithm, and Facebook is actually probably the main guilty party, because this, you can see this polarization has risen very strongly, and it coincides almost exactly with the rise of Facebook. Strange, huh? So there's a lot of study on this. Actually, I have a student working on this. Because Facebook doesn't care about polarization, they care about engagement. So the algorithm maximizes that you come back and they want you to be addicted, okay? And this can last for a very long time. How can this inconsistency last if there's communication? Well, maybe you have this tightly knit community in the middle between the two pieces, a very opinionated nodes. Maybe each node, the majority around it believes A, and then you have another node, the majority believes B. So the node that believes A will not accept B, and vice versa. The information will not pass, okay? There are techniques to overcome it, and this is one of the big problems in internet today, okay? Not solved yet. Hopefully we survive. And we have not even solved this one, and we get another problem, ChatGPT, but okay. Final thing is something that's really important that you have to understand. All large networks created from the real world, organically, from humans. If the data comes from humans or from the real world, it will be a small world graph. So that means a graph where the distance between any two nodes is small, which means the shortest path between any two nodes will be small, and also it's clustered, it's compact. That seems contradictory, but it's not. So you can actually navigate easily in these graphs. People talk about 6 degrees of connectivity and stuff like that. And the graphs have a power law structure. So there's the number of people that are popular. So K is a measure of popularity. The more popular you are, the fewer there are. So it's proportional to 1 over K squared. That's actually very big, and it only goes down very slowly when K increases. So you have these influencers, people with a huge popularity in this thing, okay? So this gives you this graph where everything's connected, and it's easy to talk to each other, but still it's local, okay? I'm sure in this room, everybody sees everybody else, but if you look at who everybody knows, it will cover the whole world in a pretty dense way. Okay, so maybe that's all I can say in the small amount of time I have, okay? Large systems must be scalable. They must be scalable, since they will be fluctuating and you will have problems. So they must be, you cannot do it otherwise. Building them is hard, okay, we know that. Principles, you have temporary overload, permanent overload, so the multiple timescales, reducing nondeterminism, and be aware of phenomena that will occur. And this is a snapshot of an ongoing project. And here, to come back to the Christmas tree, so there's some references you can look at if you want more information on this. Okay. I actually gave a one-day tutorial in High Peak in January. So you can find the slides on the internet. And we're also formalizing, because we want to build tool support. We want people to build systems using these approaches, okay? Okay, I think I stopped there. I think I've jiggled your neurons enough. Thank you.